So here we will discuss the second method of converting a decimal number into binary form, which is the repeated division by 2 method. Now this method is based on the basic concept of mathematics, okay, which is exploited here, is that if we divide a even number, okay, a even number by 2, it will be completely divisible and the remainder will be 0, okay, if we divide an even number by 2. But if we, okay, for example, if we divide 8 by 2, it will be 4 and the remainder is 0. If we divide, let us say, 18 by 2, it would be 9, the quotient, the remainder is 0. 256 by 2, it is 128, the quotient, and the remainder is 0, okay, and so on. The remainder is always 0 when a number is an even number is divided by 2. But when an odd number is divided by 2, okay, an odd number is divided by 2, the remainder is 1, the remainder is 1. So you see the concept here, we want to get ones and zeros, a string of ones and zeros. That's why we are dividing a particular decimal number by 2. So there are two possibilities, either we will get a remainder 0 or remainder 1. Let us say we divide 19 by 2, we get 9 as quotient, we get 18, remainder is 1, this is the remainder. Suppose we divide let us say 25 by 2, this is 12, this is 24 and this is 1, remainder is 1. Suppose 257 by 2, 128, 256, remainder is 1, this is the remainder. So always when we divide an odd number with 2, we will always get a remainder as 1. So we need a string of ones and zeros because binary numbers allow only ones and zeros. So that's why this repeated division by 2 concept or this method came into play. So let's see how we can use this method to convert any given decimal number into binary form. Okay. So let us take a simple number first. Let's say we take 9. Okay, we take a simple number 10. For the purpose of making you understand, I am taking 9. We can take higher number, but let's just start with 9 and we have to convert it into binary form. So in the repeated division by 2 method, what we do is we take 9, we divide it with 2. So we get 4. If we multiply 4 with 2, we will get 8 here and we will get remainder as 1. This remainder 1 goes outside, okay, 1, it goes outside. This 4, this quotient, it goes here, okay. So we again divide this quotient that we get with 2. This time it will be 2, the quotient, minus 4, the remainder is 0, okay. Again this remainder, it goes outside, it goes outside. Next this 2, it goes here, 2. If we multiply 1 we will get 2, it is 0. Okay, we will get 0, and this 0, okay, this 0, it goes outside, this 0, it goes outside. Now this 1, again, two, if we multiply it with 0, okay, it will be 0, and this output it will be 1, okay, it will be 1. So the concept here is that you have to proceed until this quotient it becomes 0. The quotient becomes 0. You have to proceed until that, and you have to note these remainders until that. Now this quotient, it has become 0. So now what you have to do, you have to proceed from downwards, okay. Here, because of the lack of space, we have to move here. So the last remainder is this 1, and you have to proceed from here, okay. You have to start from here and you have to move upwards in this direction, and note the digits in that order. First is 1, we have to proceed upwards in this way, we have to proceed upwards. So the first digit that comes is 1, next is 0, 0 and 1. So this is the given binary number 1, 0, 0, 1, the binary representation of the decimal number 9. So this is the repeated division by 2 method. You divide the given decimal number with 2 first, note the quotient, note the remainder, the quotient goes downwards, again you divide it with 2, note the remainder, again the quotient goes downwards, again the quotient here is 1, you divide it with 2, the quotient is 1, the remainder is 0, again you divide it with 2 until the quotient becomes 0. If you multiply 2 with 0, the result will be 0, and if you subtract it, the remainder will be 1. So here the quotient becomes 0. So here our repeated division, it stops, because you cannot perform 0 by 2, there is no sense in that. So you have to wait until the quotient becomes 0. Then we are interested with the remainders. I told you, whenever we divide an even number with 2, the remainder is 0, with an odd number the remainder is 1. So we are interested in the remainders. Then we proceed from the last division towards the first division, the remainder of the last division to the remainder of the first division, and we note the binary digits in that order: 1, 0, 0, 1, 1, 0, 0, 1, and we got the binary representation of the decimal number 9. Okay. So let us take another example. Let's say 45, the decimal number 45, and we have to convert it into binary form. I will do it using the repeated division by 2 method. So here first we divide the decimal number 45 with 2, the quotient will be 22, we will get result as 44, and the remainder will be 1. Okay, the remainder is 1. Again this 22, it goes to 11, is 22, it is 0. So the remainder is 0. Again this 11, it goes down, again it is divided by 2, the quotient is 5, result is 10, the remainder is 1. Again this 5, it goes down, okay, the 5, it goes we divide it with 2, okay, and this is 2, this is 4, the remainder is 1. Again this 2, it goes here, we divide it with 2, this is 1, this is 2, this is 0, the remainder is written again, this 1 again. Now here the quotient becomes 0, the quotient becomes 0 and the remainder is 1. Okay, so this is the remainder of the last division performed, division by 2. This is the remainder of the first division which is performed. So we have to proceed, okay, from the last, okay, up to the first, and we have to note the remainder bits, ones and zeros, in that order. So we'll start from here: 1 0 1 1 0 1, okay, 1 0 1 1 0 1. So 45 decimal is equal to 1 0 1 1 0 1 in binary form. Always proceed from the remainder of the last repeated by 2 division up to the first remainder, okay, that is the correct order. So 45 decimal number in binary form, it is 101101. Sometimes the repeated division by 2 method, it can occupy a lot of space and can become quite lengthy to perform it, but we will use the same concept and we will implement it in a different way. So let us this time take a decimal number more than 100. Let us say we take 256, okay, and we have to convert it into binary form. So what we will do is that we will take 256, we will divide it with 2. Now we will find the closest largest multiple of 2 which gives us 256. So if we multiply 2 with 128, we will get 256, and in this process the remainder is 0. Okay, 2 into 128 is 256, 256 is exactly divisible by 2, it is an even number, so the remainder is 0. Again 2 into 64 is 128, so the remainder again is 0. Again the 64 is divided by 2, 2 into 32 is 64, the remainder again is 0. So you see here we are dividing the given decimal number with 2, and again we are dividing the quotient. This is the quotient, 2 into 128 is 256. In the repeated division method, this is the quotient. Again we are dividing with 2, again this is the quotient, again we are dividing with 2, and we are noting the remainders here in this side. This is the remainder. We are implementing the same repeated by division 2 technique, but in a different way. Again 2 into 16 is 32, the remainder is again 0. 2 into 8 is 16, the remainder is again 0. 2 into 4 is 8, the remainder is again 0. Okay. 2 into 2 is 4, the remainder is again 0, and 2 into 1 is 2, and the remainder is again 0. So in this method you have to proceed until you get this quotient as 1, and you stop there. You stop once you get this quotient as 1, and then you proceed including this 1 upwards. You proceed upwards and you note these remainder bits, the binary digits, which is the given binary number, the binary equivalent of this decimal number 256. So 256 decimal in binary form is 1 with 1 2 3 4 5 6 7 8 zeros. Okay, this is the binary representation of the decimal number 256. So this method comes in handy when the given decimal number is more than 100, and we can easily convert the given decimal number into binary form. Okay. So we are performing the same thing that we performed in repeated division by 2. Okay. Here when we divide 256 by 2, the quotient will be 128. Okay. So again we divide that quotient that we got with 2, again the quotient 64. When we divide 128 by 2, the quotient is 64, and we note the remainders simultaneously. Again we perform the same thing until we get the quotient as 1, and we stop there, and then including that quotient at the bottom, we move upwards and keep on noting the remainder bits, and in that order we write the given binary equivalent of that decimal number. Okay. Now let us take another number. Let's say an odd number we will take this time. Let's say 125. Okay, decimal number, and we have to convert it into binary form. Okay. So again we will do the same thing. 125, we divide it with 2. So it will be 62. 2 into 62 is 124. So the remainder will be 1. Again 2 into 31 is exactly will give us 62. The remainder will be 0. Again 2 into 15 will give us 30. So the remainder in this case is 1. 2 into 7 will give us 14. 2 into 7 will give us 14. So when we subtract 14 from 15, the remainder will be 1. Again 2 into 3 will give us 6. So when we subtract 6 from 7, the remainder will be 1. Again 2 into 1 is 2. So when we subtract 2 from 3, the remainder will be 1. Now once we reach this 1, we will stop then and there, because we have reached 1. Then we will move upwards. We will move upwards and we will keep noting the remainder bits. So it will be 125, okay, in decimal form can be written as 1, 2, 3, 4, 5, 5 ones, 0 and a 1 in binary form. Okay. So here we have taken an odd number and we have converted into binary form. Now so far what we have discussed is that how to convert a whole decimal number into a binary, its equivalent binary form. But suppose we have to convert a decimal number with a fractional part, or a fractional number in decimal form into binary form. How to do that? Now let us say we take a fractional number, let's say 0.45, which is in decimal form, and we have to find out its equivalent binary representation. Okay, we have to find out its equivalent binary representation. So how we are going to do that? So for that, you take that given fractional number and you multiply it with 2. You multiply it with 2. Here 0.45 into 2 is 0.9. Okay. Now in this 0.9, only consider the digit which is to the left of the decimal point. Only consider that digit which is to the left of the decimal point, and you take it here, you write it here, it is 0. This is important. The remaining, which is 0.9, again you multiply it with 2, it will be 1.8. Again, you consider that digit which is immediately to the left of the decimal point and you take it and write it here, it is 1. Again, the remaining, after you take 1, the remaining which is left is 0.8. 1.8 minus 1 is 0.8. Again, 0.8 into 2, which is 1.6. You take this digit and you write it here. Okay. Now, you do that at least up to 3 decimal places, or you repeat it 3 times. This is required. Okay. You can go even further, but you do it up to 3 decimal places, means 3 times. Now, you start from the top, okay, the top, and you move down. In case of whole decimal numbers, we proceeded upwards, but in case of fractional decimal numbers, we proceed downwards. So 0.45 in decimal form, we proceed downwards and keep on noting these ones and zeros. It is 0, 1, 1, okay, is 0.011 in binary form. 0, 1, 1, we have proceeded downwards. First comes 0, then 1, then 1, 0.011. 0.45 in decimal form is equal to 0.011 in binary form. So this is the way to convert a fractional decimal number in fractional form into its binary equivalent. Okay. Suppose we take another fractional number, let's say 0.3125, which is in decimal form, and we have to convert it into its equivalent binary form. So we'll perform the same steps. 0.3125 into 2. Okay, so it will become 0.625. Okay, 0.625. You consider the digit to the left of the decimal point and you take it here, it is 0. Again, 0.625 into 2 is equal to how much? 1.25. 1.25. So you take this 1, write it here. After you have taken 1, the remaining value is 0.25. 1.25 minus 1 is 0.25. 0.25 into 2 is equal to 0.5. You take this 0 here, write it here. Let us proceed to another decimal place. 0.5 into 2 again is 1.0. So you take this 1 and you write it down here. Now, starting from the top, we'll move downwards. We'll go downwards and we'll note the bits in that order. So 0.3125 in decimal form is equivalent to 0.0101 in binary form. 0.0101. Okay, so this is the conversion of a fractional number in decimal form into its binary equivalent. Okay, so this is the way you do it. In a whole number case, we moved upwards. Here it is downwards. We are multiplying. There we were dividing with 2. Here we are multiplying it with 2. That is the only difference. Suppose we have a number which consists of both a whole and fractional parts, okay, in decimal form. Let's say 496.35, and we have to convert it into its equivalent binary form. So for that, what we have to do is that we have to separate the whole and fractional parts. 496.35 can be written as 496 plus 0.35, and we have to deal with them separately. So this 496, the binary representation of 496.35 is equal to the binary representation of this 496 plus the binary representation of 0.35, and you have to do it in that way. Okay, so let us do it. First we will consider 496, okay, the whole part, 496. So 496 will do, so it is 248. If we multiply it with 248, the remainder it will be exactly divisible and the remainder will be 0. Again 124, if we multiply it with 2, the remainder will be 0. Again if we multiply it with 62, the remainder will be 0. Again 31, the remainder will be 0. Again 2 into 15 is 30. Here 31 minus 30, the remainder is 1. Again 2 into 7 is 14, 15 minus 14 is 1. 2 into 3 is 6, 7 minus 6 is 1. Again 2 into 1 is 2, 3 minus 2 is 1. Okay, and once we reach 1, we will stop there. We will stop and we will move upwards. So 496, okay, 496 is in decimal form, which is in decimal form. Its binary representation is 1 2 3 4 5, 5 ones followed by 4 zeros. This is its binary representation. Okay, so this is the for the whole part. Now for the decimal part, we'll do it here. 0.35, we'll multiply it with 2. Here we are dividing it with 2. For the fractional part, we'll multiply it with 2. So it will be 0.7. We'll consider this 0 and we'll take it here, we'll write it as 0. And again 0.7 into 2 is equal to 1.4. So we'll take this 1 and we'll write it here. Again, if we take out 1.1.4, it will be 0.4 remaining. Into 2, it is equal to 0.8. So we take this 0, we'll write it here. Okay, so let us just move another place forward. 0.8 into 2 is equal to 1.6. So take this 1, move it here, it will be 1. So you have to proceed up to 3 decimal places. So it is sufficient up to here. So if you want, you can proceed one more, and then we will move downwards. Here we moved upwards, you see. Here we are moving downwards. So 0.35 in decimal form, it can be written as 0.0101. Now we have to combine them. Okay, so if we just remove all this, so 496.35 in decimal form, it can be written as 1111000.0101 in binary form. This is the answer. So you have to deal with the whole and the fractional parts separately. You take the whole part, you convert it into its equivalent binary form, you take the fractional part, you convert it into its equivalent binary form, and then you combine it. Okay, so here we have discussed the various methods of conversion of a decimal number or a base 10 number into its equivalent binary form. Okay, so in the next set of videos we'll discuss the opposite, how to convert a binary number into its equivalent decimal form. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.